Chapter 18, for most chemistry students, I think, is not just one of the longest chapters in the book, but it is one of the hardest chapters in the book in terms of all the different kinds of equations and some of the math problems that go with it. As a result, we're going to take our time going through Chapter 18 and have two tests. A test over the first half of the chapter and a second test over the second half of the chapter. Now, you might recall that back in Chapter 3, we talked about 4 different kinds of reactions: acid-base reactions, precipitation reactions, gas-forming reactions, and redox reactions. This chapter focuses on weak acid and weak base types of reactions, and it also focuses on KSP reactions. Those are the two halves of the chapter, if you will. And then in a later chapter, we're going to do electrochemistry, which is the oxidation reduction reactions. So, our goal in this chapter, first of all, is to answer the question, how can we control the pH of the solution? Let's reflect for a minute on this word control. Control, regulate, harness, put to use, take advantage of. These are all aspects of the Genesis 1 idea of having dominion, or to rule over, that Adam and Eve, and through them, you and I, are charged with. We are to have dominion. But keep in mind that dominion does not mean to stomp on or to treat any way we feel like it. The concept of dominion in Scripture means stewardship, the wise use of. To use it in a way that we know that the person who left us in charge of it, the Creator himself, would want us to use it. So that's something to be on the lookout, because we see this kind of word all the time in science. And you might then ask the question, well, why would we want to control the pH? There are lots of chemical reactions that are very, very sensitive and take place better at one particular pH and don't take place very well at lots of other pHs. So it's really helpful to be able to control the pH. A little bit later in this chapter, we're going to deal with a concept called buffers. That's mentioned down here. And buffers are combinations of substances which help to keep the pH from changing very much, which is also very important. A lot of biological systems are extremely sensitive if the pH were to change. And of course, in living things, pHs could easily change if the living organism were to become sick, become infected, become poisoned, be wounded, be stressed. All of these kinds of things can alter the pH of that living system. In animals and in humans, even a dramatic change in your diet can affect the pH. So we want the pH to remain very constant. We'll talk about that in the next lesson. This is lesson 1 for chapter 18. We also want to see what happens and be able to predict the result of any acid or base combination that we might choose to mix. Now, by the way, one of the examples of mixing acids and bases is called a titration. And you have done some titrations already. Often it's using your drop counter, which seems to have about a 50% success rate. And hopefully we'll get better at that with some newer drop counters in our titrations. So those are some of our goals. If you look at the next 3 bullet points, if we have a water solution of 2 ionic compounds and we mix them, will we get a precipitation? This is part 2 in the chapter. Right now we're working on part 1. Part 2 in the chapter will go with test 18b. Part 1 goes with test 18a. So, in order to understand buffers, we have to begin by thinking about the common ion effect. Now, the word common here does not mean everyday or ordinary. It doesn't mean commonplace. The word common here means to have something in common with. For example, everybody in the AP chemistry classroom has in common their chemistry teacher. And of course, obviously, you all have in common a great love for chemistry. At least I hope so. So that's what we mean, to have in common. And in particular, we're talking about an ion that two different chemicals will have in common. And those two chemicals would be a weak acid and a soluble salt containing its conjugate base, or a weak base and a soluble salt containing its conjugate acid. Because that would mean that the conjugate would be present in both the soluble salt and the weak acid or base, as you'll see in a minute. And the result of having these two chemicals together in the solution at the same time is what we call the common ion effect. And in a sense, it's the basis for understanding buffers, which help to keep the pH from going too high or too low. And that statement right there is kind of a tip-off or preview. If you want to keep a solution's pH from getting too high, you need a chemical to do that. And if you want to keep the pH from getting too low of that same solution, you need a different chemical to do that. In other words, you need two chemicals present at the same time to accomplish the two tasks of keeping the pH from going up and keeping the pH from going down. And these two chemicals need to have a common ion, an ion in common between them. So here's our first example. Let's suppose we have the weak acid, acetic acid, and we're going to hydrolyze it so that polar water is going to yank the hydrogen right there away from the acetate, which is right there. And so my acetate is now there, and my hydrogen connects to the water molecule. The hydrogen from there connects to the water to make this, the hydronium ion. So I have my weak acid, which means my water is acting like a weak base, and my acetate ion on the right becomes my conjugate base, because it's what's left behind after the weak acid has donated a proton, and this is my conjugate acid. Acids are acids, whether they're conjugates or not. Conjugate bases are bases and have the same properties as any other base. So, this over here is a beaker in blue. So let's write that word so you know what that weird looking thing is. That's a beaker. And let's suppose we're going to put some weak acid into the beaker. When we put some of this acetic acid into the beaker, we are going to have this, C2H3O2. Notice I'm writing my acid differently than your book did, to kind of show the hydrogen ion and the acetate ion as being connected. And you're going to have lots of these because of the fact that when you put acetic acid in water, acetic acid is a weak acid, so it doesn't split up much. It only splits up a little bit. So you're going to get a few H3O pluses, just a few, because it's only going to go to the right a little bit, and you're just going to have a few conjugate bases, C2H3O2, negative charge. You're just going to have a few of them. But now let's suppose you come along and you're also going to add some sodium acetate. Sodium acetate is a soluble salt. It's a sodium salt, and acetates are soluble. It's a soluble salt containing acetate. Acetate is the conjugate base of the weak acid acetic acid. Now we can ignore the sodium because it's a spectator. So in a sense, you're putting lots of, oh, thank you, eraser. Just erased my nice, lovely beaker. We're going to be putting lots of acetates in here as well. So instead of having just a few, I do not know why it keeps erasing on me, but instead of having a few C2H3O2, we now have lots of them because we've added sodium acetate. We still only have a few H3O+, because the only place they came from is the dissociation of my original acetic acid, which is a weak acid, and that doesn't have much. So you'll notice that now we have lots of acid and lots of conjugate base. And so what this means is because I have lots of acid, it can neutralize the addition. If someone were to come along and add a base, it could neutralize the base and keep the pH from going up, which is what normally happens when you add a base. And because we also have lots of base, the acetate ions, it's the conjugate base. Since we have lots of base, if someone tries to make my pH go down by adding acid, my base can neutralize that acid and keep the pH basically constant and the same. Now, obviously, if you add gallons and gallons of additional acid or gallons and gallons of additional base, then, of course, the system can no longer keep up and it won't operate and the pH will change drastically. This is the result of what we call the common ion effect. It's a very important concept. You may need to go back and listen to this screencast a second time and think about it carefully. Now, let's imagine that we have a weak acid, acetic acid, in one flask, and we have my sodium acetate, which is a soluble salt containing the conjugate base. The acetate is the conjugate base of this weak acid. Those in separate flasks. And they're kind of color-coded there with an indicator to distinguish them. We would know that my weak acid would have a pH less than 7 because all acids in solution have a pH less than 7. It certainly isn't going to be a pH of 1 because it's not a strong acid. Now, my conjugate base came from sodium acetate. And sodium acetate, you could pretend that sodium acetate, whether it did or not is irrelevant, sodium acetate is possibly the product of the strong base and a weak acid. Acid plus base, here's my base, here's my acid, makes a salt, sodium acetate, and water. You remember that from honors chemistry. Well, if you remember, a strong base wins out over a weak acid, which means that sodium acetate is going to have a pH greater than 7 because it's a strong base winning out over a weak acid. So that means that here I have my pH less than 7. Here I have a pH greater than 7. And when I mix the two together, I should get a pH somewhere in between. Not as low as 2.7, but not as high as 9. And if you look at the meter reading, it's a little less than 5. And of course, it could be other readings too, depending upon the volume and the concentration of your acid, of your salt, original solutions. Now let's do an ice chart here. Let's imagine, let's see where that problem begins. Okay. Let's imagine that we have a 0.25 molar solution of acetic acid, my weak acid. Okay? And let's imagine I also have a 0.10 molar of my sodium acetate, which is my soluble salt containing the conjugate base acetate of my weak acid. And we're about to put them both into a beaker at the same time. So these are my initial quantities per liter of weak acid and sodium acetate. Now, because of the fact that I don't have any hydroniums yet, because we're pretending that we haven't allowed the weak acid to begin to dissociate or to react with the sodium acetate, and now we say go, and the reaction has to go to the right, because basically this value here is so small it's basically 0. It has to go to the right. It can't go to the left, which means this is going to be a minus x, this is going to be a plus x, this is going to be a plus x, because you have a 1 to 1 to 1 to 1 ratio. It's all, I'm sorry, this is where that's supposed to be, a 1 to 1 to 1 to 1 ratio. So it's minus x and plus x. So as a result, here's my concentration of acetic acid at equilibrium, the concentration of hydronium at equilibrium, the concentration of my conjugate base at equilibrium. And so we write our equilibrium equation. We write our equilibrium expression, putting the products over the reactants. And then we plug in our numbers and grind out the math. Now, it would be nice if we didn't have to worry about this plus x and minus x. It'd be nice if we could just get rid of this and get rid of that. Well, let's perform our test. If we multiply my equilibrium constant by 100, I get 10 to the minus 3. And 10 to the minus 3 is still smaller than either one of my original molarities, which means I can go ahead and ignore the plus x and the minus x, and so my equilibrium expression is now simplified. It's much easier to do mathematically, and we can solve this equation for x. When we solve it for x, we find out that the molarity of x, which is my hydronium ions, is 4.5 times 10 to the negative 5. You'll notice there are two significant digits. So when I take the negative log of it, I need two significant digits. Remember, after you take a logarithm, the significant digits are always the numbers after the decimal point. And there's your two significant digits. Your pH is 4.35. Keep in mind that you got Le Chatelier's principle at work here. Adding that common ion causes the reaction to proceed less far to the right than it would normally proceed. Normally, this would go to the right a little farther, because before you added the sodium acetate, this value was 0. But because now you have sodium acetate in there, it doesn't go to the right quite as much. You don't make quite as many hydronium ions, and so your pH, instead of being 2.7 up here, it is higher than that, 4.35. And again, you might want to go over that one more time. The last example, what is the pH of the solution that results from adding 25 mils of a strong base to 25 mils of a weak acid? Technically, this would be considered a titration of sorts. And you're giving the equilibrium constant for that lactic acid, which is the acid that's in sour milk. Lactose is milk sugar. This problem has two parts to it, the stoichiometry part and the equilibrium part, which you're used to. You haven't done the stoichiometry part in a while that looks like this, where you have to find your limiting reactant. In other words, just because you mix two chemicals together doesn't mean one of them will not be in excess compared to the other. In fact, that's probably more often the case unless you jerry-rig it ahead of time so that you have exactly equimoles of the two chemicals that you're adding together. So the stoichiometry part says, well, let's find out what our limiting reactant is first of all. And you'll notice it looks like there's a piece of speck of something that was left on the copy machine when I was photocopying the textbook. So that would only bother those of you who are kind of nerdy, and I wonder who that might be. So, in order to find out which one we have in excess, just like we did way back in October, we have to find out how many moles of each we have. And so you have to take your volume times your molarity. And just as a strong hint, anytime you see both the volume and the molarity of the same compound, you're going to be multiplying those two together. 99.99 times out of 100, you'll be multiplying them together to get moles. We do the same thing with the lactic acid. Volume times molarity. And you'll see that I have twice as much lactic acid as I have sodium hydroxide. So therefore, the sodium hydroxide is my limiting reactant, the one that limits the reactant, the one that I run out of first. Now, once we know that, we can, which is what we did right here, we can find the amount of lactate ion produced by the acid-base reaction. So we take our limiting reactant, we have this many moles, it's in a 1-to-1 ratio with my lactic ions. So this is the most lactic ion. Remember, this is the conjugate of the weak acid. This is the most lactic ion that I can produce in a reaction with sodium hydroxide. The few lactate ions that you could produce from the dissociation of lactic acid, which would happen if it were all alone, is negligible. That's why we don't worry about it. Not to 2 or 3 sig digs. You're not going to have any lactate ions coming from the dissociation of lactic acid in the water. Now, the next thing that we're going to do is recognize then that if that's how many lactate ions are produced, that's going to be how many lactate acid molecules must have been consumed, because they're in a 1-to-1 ratio. For every lactic acid molecule that reacted with sodium hydroxide, you got 1 lactate ion, 1-to-1 ratio. So now we come down to letter D, and so we can say we started off with this many moles of lactic acid, this many moles reacted with the sodium hydroxide, this leaves this many moles of lactic acid unreacted. That's how much is in excess. Now, when we come to letter E, there's a very important point here. This is a step that is frequently forgotten by students. Anytime you mix two solutions together, you are diluting both of them. So you have to take your new number of moles of lactic acid that you have as a result of reacting with sodium hydroxide, the lactic acid molecules that are left over, and divide it by the new volume, the sum of the two volumes. Remember the sum originally, pick a different color here, you had this volume, and when you add it together, you get this volume. So you take the number of moles of lactic acid, which is half of what you started with, divide by the new volume, and here is your new molarity of the lactic acid. And that's also the new molarity of the lactate ion, because again, it's a 1-to-1 ratio. You take that 1.25 times 10 to the minus 2 molar lactate ion, moles of ion, and divide by the new volume, and you get the same molarity. So in my ice chart, I'm starting off with both my weak acid and my conjugate base of that weak acid. So in other words, I'm starting off with an acid and a base in solution. The sodiums are long gone. They're just spectator ions now. And the reaction has to go to the right because I have basically no hydroniums to speak of, except maybe a couple from the autoionization of water, which are irrelevant here. The reaction will go to the right. Minus X plus X plus X. So we have our equilibrium equation, step 1. Our equilibrium expression, step 2. We fill in the values from my equilibrium. Fill that in. And once again, we have to make a decision. We have a plus X and a minus X. Wouldn't it be nice to get rid of them? Well, let's double check. I have 10 to the minus 4. I multiply by 100. I get 10 to the minus 2, which is 0.01. And 0.01 is less, more than half is much less than half, or it's less than half as much as 0.025. So we're getting close, but we can't ignore the minus and the plus X. We can ignore that. And so now when we solve for X, X of course is hydroniums. The negative log of my hydronium molarity gives me a pH of 3.85. Remember, lactic acid itself is 2.73 if you were to take the negative log of the original molarity before adding sodium hydroxide. And so like you might expect, anytime you add a base to an acid solution, the pH is going to go up. But notice it did not go up nearly as much. It just went from 2.73 up to 3.85 instead of all the way up to a 7 or 8 or a 9. Now, in lesson 2, we'll start talking about buffers.